this is really fast. How many TA sections do you have?
This is for the whole class.
For the whole class, though. So it's a lot. So was it the state class test that they took
I didn't know that they put that on there, so probably. Yeah, since you didn't need it on last exam.
Oh wait, no, it wasn't like it was the size.
Oh, yeah, no, I don't think it was a mistake. Maybe it was. Okay, guys, we're going to go ahead and get started. Actually, is your laptop still recording? It just went blank, so.
Oh yeah, it is.
Oh. Okay, so I'm recording this, but it's not very zoomed out. So if I start writing on like either of those whiteboards, maybe someone stop me and have me just erase something and then continue to write on these two whiteboards. Yeah.
I've got a quick question about the practice exam.
Okay.
So on the practice exam, this on learning suite, there are, I think, 4 fewer multiple choice questions and 2 fewer written questions than there are on the key to that same exam.
Okay.
Do you know anything about that? Why they were taken off? Do we need to know that?
That's probably because last semester there was slight rescheduling in how the exams are. So, for example, they added another exam, and so each exam had less material on it. So that's probably why.
So you're saying we should know the stuff that is not on the practice exam but is on the key?
It depends on what's on the key. I don't know what was taken off.
Okay.
So,
I was just wondering.
yeah. Sorry, not positive. Cool. Okay, so we're going to go ahead and get started. But just a disclaimer for this review and for this unit in general. So there is going to be a lot of questions that, in all honesty, have required your practice in order to do things. So, like Lewis structures, right? If you don't know how to draw Lewis structures at this point, I'm probably not going to be going over that in this review. Because, I mean, that was like a full, 2 lectures that we did that on. Of course, I'm going to have you guys practice Lewis structures and then see if you get the right answer. But this test is a lot of either you kind of know it or you don't. And then I will point out a few conceptual questions that you are likely to be asked that do require a little bit more maybe teaching. But there is a lot of, for example, naming. There is a lot of practice problems in this review because hopefully the practice will help you understand how to do things. And I'll go over the naming rules if you want to, but it might take a little while to just do that naming. So more likely this review is going to be a lot of practice problems, and then if you would like to go over specific problems, we can go over why and the rule that applies to that. But just don't want to be here for 3 hours, you know? So just a few things, like the slides say, you'll be given an electronegativity table. You don't have to memorize those. Just a few things that you should remember how to do from last exam, but that you probably already know how to do. And then making sure you memorize those polyatomic ions and common elements, all right? So any questions before we get started? Okay, so we're going to actually start with the most recent material: bonding, valence bond theory, and molecular orbital theory. So for bonding, each individual bond has a polarity. We most recently talked about molecules and whether they're polar or nonpolar, but this is different, okay? This is just each individual bond. So to determine whether a bond is polar or nonpolar, you take the electronegativity difference with the information right here. So ionic, polar, and then nonpolar. So there's also just this definition on here that you should probably know, that all chemical bonds and intermolecular forces, that's actually a topic that won't be on this exam, it'll be on next exam, but they're all held together by what's called electrostatic attraction, and that lattice energy increases with increased charge and decreased size. And we'll go over an example of lattice energy in just a second. But any questions on bonding? Pretty straightforward, you just are taking the electronegativity difference. Yeah?
Sorry, this is for lattice energy though. Like, so they say it depends on its increased charge and its decreased size.
Yeah.
But like, for example, like I think it was on the practice test, it said it was potassium, sodium, calcium, magnesium.
So you're asking for priority, which one takes priority, charge versus size? Yeah, so charge is more important.
Charge.
If they have the same charge, then you will look at the size. And we're going to see that with this example right here.
So you first look at the charge of it first, and then you go to the size.
Correct. Yep. So we'll go ahead and do an example of what he was asking in case you didn't hear him or understand what we were talking about. We'll see that in this practice problem right here. So I'm having you order the compounds from smallest to largest lattice energies, remembering based off of charge and size. Okay, so you got your periodic table up there. Okay, so what's our charge of LiCl? +1, -1, right? What's the charge of MgO? +2, -2, NaCl. And then MgCl2? +2, -1. Because chlorine has a -1 charge. You guys, some of you said +2, -2 because there are two chlorines. That doesn't matter because we're talking about one bond. So even though there are two chlorines, because we need two chlorines in order to neutralize the whole molecule, there will only be, we're looking at just from one Mg to another Cl. So we know off the bat which one is the strongest. MgO, because MgO has +2, -2. Which one's the second strongest? MgCl2. All right, but now we're ranking the two that have the smallest lattice energies, LiCl and MgO. Both have +1, -1 charges, so how are we going to rank them? Well, we're going to say that the stronger one is going to be, what did we just say? The one with the smaller size. So what's smaller, LiCl or MgO? Oh, I'm sorry, LiCl or NaCl? LiCl, right? So that's why we have the order like this. Are there any questions with that? Okay, great. Those ones pretty straightforward. Okay, so for molecular orbital theory versus valence bond theory, there will likely be a few questions, maybe like 2 questions on the multiple choice part that asks you to differentiate between, well, no, it won't directly ask this, but you need to know the differences between valence bond theory and molecular orbital theory. I'm not going to go too into detail in those, but you can find that information in several different locations. he has 3 different slides on his lecture PowerPoints that talk about advantages and disadvantages of both valence bond theory and molecular orbital theory, and 1 slide that compares the 2 side by side. So know those slides. There is also on both of your problem sets that cover valence bond theory and molecular orbital theory, it talks about what valence bond theory can do. Can it predict bond orders? Can it predict molecular geometry? Can it predict bond energies? And it goes into that a bit. So just take a look at the keys. Know which one does which, and you should be fine. Know what valence bond theory is, right? That valence bond theory is describing when 2 atomic orbitals hybridize, and that when they come together, they are either head-on-head overlapping to form a sigma bond, or that there's overlap above and below for a pi bond. If you know those general characteristics of valence bond theory, molecular orbital theory, and those differences where I just told you where you can find those, you should be fine. Are there any questions about that, though? Anything that I can elaborate a little further on? So these are one of those questions that are a little more conceptual, and what you just need to do is you need to just look through his lecture slides, making sure that you are including those in your studying. He has several sections on his lecture slides that are like, molecular orbital theory can describe this, and then it goes on to describe it. So just make sure you know those. Go through his lecture slides. Yeah?
So valence bond theory, honestly, is like probably one of the only things it's good for is geometry. Like it's like or like the shape.
Yeah, it's helpful. Yeah, valence bond theory is helpful in describing how geometries are able to be the way they are according to Vesper. Correct, yeah. Because MO theory does a lot more for us. Okay, any other questions? Okay. So, getting into some of the aspects of each of these, all right? A little more of the practical problems. So, valence bond theory, we have sigma bonds and pi bonds. How many sigma bonds and pi bonds are in the following molecule? With the reminder that a single bond is going to be how many sigma, how many pi? 1 sigma, 0 pi. A double bond?
1 sigma.
And then a triple bond?
1 sigma.
Okay, perfect.
Is that supposed to be a triple bond there on the left?
Yes, that's a triple bond right there. What?
Did that work?
Will that work?
There's like a triple bond and double bond.
So that is just representing a triple bond. Oh, what do you mean? Doesn't matter where? Oh, so do you think the triple bond is attached to the double bond?
So it's attached to that carbon, right? That's attached to the double bond.
Yeah. So it's attached to a carbon, which is single bonded to a carbon, which then has 2 double bonds coming off.
Oh,
That's a little bit of a tricky part, so you'll see that in just a second.
so okay, so there would be a carbon, and a carbon, and a carbon, and a carbon. So there's 4 on that last line there.
Yep.
Okay.
Okay. So, who got way less than 26? Okay, as my students could probably attest, I love telling people that they're wrong, okay? So you're all wrong, all right? Those of you who said less than 26. Now, I love telling people they're wrong because that's the best way for you to learn it. So if you got that wrong, you absolutely better be writing that down right now, okay? Because that is tricky. Forgot about the implicit hydrogens. That's likely why you got less than the 26 sigma bonds that there are. So, please write that down if you got that wrong. Remember that there are implicit hydrogens, which are all single bonds, so there are sigma bonds there. Also remember, if you can see my mouse, because I don't think I can figure this laser point. Okay, no, it's working. Okay, so also notice if I can get my hand steady, right? This is a carbon right here. That's a carbon, that's a carbon, and that's a carbon. Kind of weird. Why do I have it drawn like that? Why? So this is a carbon, this is a carbon, this is a carbon, and this is a carbon. Why on earth have I done that? Why aren't I doing this? Like we normally see it. You will never, ever, ever see it like this because this is very wrong. Someone tell me why it's very wrong that you'd see it like that. Yeah?
Molecular geometry is linear.
Because triple bonds are linear, right? The steric number of this carbon is 2. So this is a linear molecule. You would never see it like this because that's not at all what it actually looks like. So, a little tricky again, but make sure you're recognizing that those are multiple carbons in that one line. Yep.
I've counted this 3 times now. I can only get 24 sigma bonds.
24 sigma bonds? Okay, so let's follow my mouse. Hopefully I didn't do this wrong.
Two vector on the triple bonds that you talked about there, probably.
So I've got 1, 2, 3, 4, 5, 6. Did I already count it?
Yeah, you're good.
Okay, cool. All right, any other questions before I move on? Okay, moving on. What is the hybridization of each indicated atom? Okay, this is the other part of valence bond theory we talked about, our hybridizations. Okay, who wants a few more seconds to be looking at this? Okay, give you guys maybe 10 more seconds before we talk about it. And maybe as a help, I've drawn what it looks like up here. A little more detailed. Yeah. So a double bond counts as a steric number of bonds. Yeah. So just like, so you may see this. This looks like this, right? 2 hydrogens, 3 hydrogens, 1 hydrogen. That's going to be trigonal type, steric number of states. Okay, guys, so a couple confusing things about this, right? Understanding the implicit hydrogens. So what's the steric number of this guy right here? 4. So it will be what? sp3, and what will the geometry around that carbon be? Tetrahedral, okay? So what's the steric number of this one?
3.
So it'll be what? sp2. Alright, this one is tricky because it didn't show the electrons. But if I'm not indicating the formal charge on that oxygen, you should be able to assume that there are 2 lone pairs of electrons right here. Why? Because, well, 6 valence electrons minus 1, 2, 3, 4, 5, 6. That's what gives me my formal charge of 0. That might be a little tricky. So if you didn't catch that, again, please write it down. So what is this hybridization? sp3. That's got the steric number of 4. Okay, are there any questions about that? Yeah.
Do you define hybridization?
Yes, so hybridization is pretty simple in practice, right? All we say is steric number of 2, sp. 3, sp2. 4, sp3, and so on, right? That's what very likely all of the tests will be. But for your edification, carbon's atomic orbitals look like this. But how many bonds do we know that carbon makes? 4. So how on earth is carbon supposed to make 4 bonds with these atomic orbitals? Because it can't share 1 electron with this one, and it doesn't even have any electrons in this one to share. So what's going on? Well, valence bond theory is a way to help describe how those molecular geometries can be working. So what we know is that it's actually going to take all 4 of these orbitals, mix them together, and spit out 4 identical orbitals, which we're going to call sp3 because there was one s and 3 p's. Now there's one electron in each orbital, and now it's able to make 4 bonds. That's the concept behind it. Probably a little more detailed than you need to know, but it's good to know in order to answer those questions of what does valence bond theory help us do? It kind of helps describe why those molecular geometries are possible. Yeah, hi James.
So we're not gonna have to do like the whole pictures that like we went over in our PowerPoints with hybridizations.
When by pictures do you mean these little things?
Yeah, like matching them to the different hybridizations.
Very, very, very likely not.
Right. I like those odds.
Yeah, again, take that as you will, but I don't know what they look like. So, again, take that as you will. Of course, with the general knowledge, they all kind of look like that, but an sp orbital will have more s character than the other ones. So maybe it'll look more like that, I think.
Okay.
So if you want to study that, you can.
Do we have to have memorized the electron geometry and the molecular geometry?
Yes, definitely.
Okay, like all the shapes, we should know like that?
Oh yeah,
Okay.
definitely. 100%. Please know your molecular geometries. You're way less likely to be asked what the electron geometry is, but you need to still know the electron geometries in order to get the correct molecular geometry, really. So, but yeah, definitely need to know that. There will be more than 3 questions about that, probably. Yeah.
Are we gonna have to be able to know like how to write the hybrid electron configurations?
Likely not. Yeah, very likely not. Actually, you're thinking of molecular orbital theory anyway, and still probably.
Oh yeah.
Yeah.
Do you know angles as well with like molecular geometries?
Yes, definitely no angles, and we're gonna go over this too. Okay, other question? Yeah.
What is the energy relationship between an SP and an SP orbital?
As in, what's the energy relationship between an s orbital, a p orbital, and an sp? Sp is right in between them, because for that reason that it's a hybrid of the 4 orbitals. Okay, am I good to move on from hybridization? Okay, so now we're going to talk about molecular orbital theory diagrams. Okay, so you do not need to know how to draw these, okay? Please don't stress out about, oh my goodness, so you'll notice even right here that I didn't include 2s sigma, 2s sigma star, 3p pi, okay? Didn't include those because I was lazy and I didn't want to, and they will give you the diagram, and what you're expected to do is fill it in, just like on your problem sets, right? On your problem sets, they gave it to you and you're expected to fill it in. Okay, that's what you're expected to do. And in all honesty, it should be pretty easy, okay? Because we've learned how to fill in electron diagrams before. So, let's give this a go. We have NO and NO+. I want you guys to tell me several different things, right? Which one has a longer bond, which one is paramagnetic and diamagnetic, and what the bond orders are. Do any of you want me to go over that information first, or just let you go get right into trying it out? Okay,
Try
cool.
it.
Go for it. I'm going to run to the bathroom, and this will probably take you a little bit of time anyway, so.
So. Truly?
The closer it is,
Okay.
well, I can show you the PowerPoint.
Bet. Bless you.
Sick of it.
I really do.
Sick of it.
Okay.
Oh, here we go. Oh, look at this.
Bond strength.
Inverse of proportional.
Is that what that means? So 1 over the bond.
Yeah, so that doesn't make sense. That's not.
Proportional to
Well, would it be one? Oh, yeah. No, that's really what makes it bad. So, okay. As you increase the bond length, how strong is it? What is stronger? A or B? Look, it's right in my hand. No. Look at it. You don't know that. Stop that. You know it. No.
You don't know that I don't know it. I just barely doing other things. Dude, I just think it's right? Look at this. And I can also.
Okay, raise your hand if you want more time. Okay, give you guys one more minute maybe. Just don't look up on the board yet. Okay, so did anyone have trouble filling in the diagram? Counting valence electrons and filling it in? Is everyone okay with simply filling in the diagram? Okay, so then of course we have our simple question of paramagnetic versus diamagnetic. The only complicated thing here is that paramagnetic makes it sound like they're all paired, right? Don't you hate that? So, diamagnetic, they're all paired. Paramagnetic means they're unpaired. So, right, this molecular orbital theory helps predict magnetism. The one on the left, paramagnetic. The one on the right, diamagnetic. Yeah.
So when you're filling pi bonds, do you put one electron in each before you fill?
Yes, just like those old rules that we learned.
So if
Correct.
there's one in each, it would still be paramagnetic.
Correct, yep, because those both are unpaired. Yeah.
How do we tell the bond length from these?
Okay, I'll go over that in just a second. Yeah.
So when in NO, all of the orbitals are have some electrons in it. So what would the LUMO be?
So I didn't include the higher ones. There are going to be higher ones. So that's why I kind of just threw that in there at the very, very end. The LUMO would be whatever one is above that one. I just forgot to include it. And HOMO and LUMO aren't as important, probably. They might not even ask that on an exam. But again, it's pretty straightforward. HOMO is the highest occupied level, and then LUMO is the lowest unoccupied one. So know those just in case. But again, probably not as important as these other aspects. So we're now going to talk about bond order. We can predict bond order by doing bonding electrons minus antibonding electrons divided by 2. So does anyone have any questions about how we got those bond orders? Okay, so 2.5 versus 3. Now, those tell us strengths and lengths. So what's stronger, a triple bond or a single bond? A triple bond, right? So those are our bond orders. So which one is the stronger bond order, 2.5 or 3? 3. Stronger bonds are shorter bonds. There's our inverse relationship again thrown in there. So they might be mean and ask you a question like that just because it tests your ability to be inverse, to remember that inverse relationship. So when I say which has a longer bond, I'm looking for the weaker bond, which would be the NO bond order, right? Okay, so did that answer everyone's questions there? So just to go off a little bit of what I was talking about earlier about knowing the differences, does molecular orbital theory predict bond orders? Yes. Magnetism? Yes. Absorption and emission spectra? Yes. Yes. Geometries?
Yes.
Okay, yeah, I'm hearing a little bit of both. The answer is you would have thought no unless you saw his lecture slides. The answer is yes, but it's just kind of complicated and something we didn't talk about. So yes, but it's more complicated. Yeah.
How does it explain absorption and emission?
So we learned, so someone answer that question for me. We learned last unit that what occurs for absorption and emission spectrum. So when energy is absorbed or emitted, what's going on? An electron is going from one orbital to an empty orbital or back. So since these are energy diagrams with empty and full orbitals, this can tell us what kind of light will be emitted or absorbed based off of that energy gap between these molecular orbitals. But instead for molecules, instead of for hydrogen, which is the only one we were doing last time. Just knowing that it can do that. You don't have to know how to do that in any way.
So if it absorbs energy, the HOMO is going to go to the LUMO position?
Yeah, those electrons from the HOMO would jump up to the, likely just the next, likely the LUMO, but it can go up to any of the orbitals. Yeah.
So this does or does not predict molecular geometry?
It can predict molecular geometries. Did I see another question? Yeah.
So generally, bonds are stronger if bond order numbers low.
Generally meaning all the time, yes.
Okay, and that also means that the bond itself is shorter.
So stronger bond is, hopefully I didn't answer that question wrong.
Yeah, I think you did.
Oh, okay, shoot, thank you. So a smaller bond order is always a weaker bond, which is always a longer bond. So small bond order is weak. Thank you for correcting me, you guys. So small bond order is weak. Large bond order is strong. Size is inversely related to that. Thanks. Any other questions? Yeah, gosh, this is being recorded. If I say something wrong on accident, let me know. Yeah.
So what does bond order represent?
The strength of the bond. So like a single bond is a bond order of 1, which is the strength, right? Single bond is, and it also describes like how many electrons are being shared between them.
Oh yeah, that's a good time.
All right, am I good to move on? Okay, so we also learned with molecular orbital theory about molecular orbitals. Know the general shape of these orbitals and be able to draw them. I'm not going to have you guys draw them and compare with your neighbor. I'm going to skip straight to the practice problem. But I want you to know where the electron density is. Okay, so for example, you know probably that this is a sigma bond, or I'm sorry, a sigma orbital, a sigma bonding orbital. But I want you guys to think about where the density is to let you know that that is a sigma bonding orbital, because not all sigma bonding orbitals look exactly like that. So, look at these 4, and now decide, and then discuss with your neighbor, which of these is pi, and it could be multiple or 1, alright? Pi antibonding, sigma, and then sigma antibonding.
Wait, this is anti-sigma, bonding sigma, anti-pi. Yeah, why is this anti-sigma? Because there's that outside. Yeah, that's what but I remember this one.
Yeah. I guess, kinda. But you should be able to infer kind of where the nucleus is, because you could very well get these pictures on a test, and you're right, they don't necessarily show where the nuclei are, but you should be able to kind of infer where they are, though. So, were there any questions that arose from this? Yeah.
So I know that it's anti-bonding when there's a node that is perpendicular to the hypersoluble axis. So it kind of looks like to me in this bottom right one that there's like kind of two nodes that are perpendicular, but I guess it's not in the middle.
Yeah, so that's why it's important to know kind of where the electron density is you can remember them kind of based off of nodes, but also electron density is helpful in understanding what kind of orbital it is. So for a sigma bond versus a pi bond, where is the electron density? For a sigma bond, the electron density is on the internuclear axis. Whereas a pi bond, it's going to be above and below the internuclear axis. So that's pretty easy to determine which of these they have on the internuclear axis, right? These two on the right. The density is right there in between instead of above and below. And again, for pi, there is a node. That one makes it a little easier. And then for anti-bonding, the electron density is in the middle if it is bonding, and on the outsides if it is anti-bonding. So for this one, right, you can see that there is electron density in the middle, okay? And that's fine. But the majority of the electron density is on the outside. So for that one, we had kind of something weird that looked like this. Right? It doesn't matter that there's electron density here. The bulk of it is obviously on the outside. Similar right here, right? There was electron density on the outside, but not much. The majority of it was in between. So that's kind of the best way to help you figure out whether it's sigma or pi, bonding or anti-bonding. Okay, are there any questions with, any more questions with this one? Okay, moving on. So some miscellaneous items for molecular orbital theory. Atomic orbitals always come together to make two kinds of molecular orbitals, bonding and anti-bonding. So he talked about this in class, looking at hydrogen versus helium. So hydrogen's a nice one to look at because it's only got one orbital, a 1s orbital, right? So if we have hydrogen and its 1s orbital, making a bond with another hydrogen and its 1s orbital, how many electrons are in hydrogen? They will come together to make two bonds, a bonding and an anti-bonding. Okay, makes sense. So I'll just put a star here for anti-bonding. So now you should tell me, with this information, why doesn't helium form a diatomic molecule? Think about it for a second and then discuss with your neighbor for like 20 seconds.
Where were you? I'm glad you guys recognize that as God.
Okay, let's bring it together. So, someone confident, tell me why helium doesn't form a diatomic molecule. Yeah.
Bond order would be 0.
The bond order would be 0. Do you guys see that? 2 minus 2 divided by 2. Okay? There would be no net bonding if helium were to come together. So it's not because it's a noble gas, all right? It's because there would be no net bonding. Yeah?
What was the net bonding with hydrogen?
It would be a single bond. So it's 2 electrons would go into the bonding molecular orbital. Yeah. Okay, so it's not necessarily probably for you to be able to draw this, but it's but knowing that helps in your understanding of why helium can't form diatomic molecules. That's the important takeaway there. Okay, so are there any questions with that? Okay, so now we're going to move on to metallic bonding, which to my understanding you have not talked about yet. You will likely be talking about that tomorrow. In like the first 5 minutes of class. It's probably just something that he didn't have time to go over yet. So, metallic bonding. Here's what's important to know for metallic bonding. As he's going to go over this in his lecture tomorrow, so I probably won't spend too much time on this, but I'll point out what you should be paying attention to in lecture. So for metallic bonding, I would know the definition of metallic bonding, according to his lecture slides. And I'll talk about what metallic bonding is right now, but keep in mind, knowing what metallic bonding is. So what we have with metallic bonding is we have all these atomic orbitals that are coming together to make molecular orbitals. So with our molecular orbital diagram, we learned that our molecular orbitals will all be in these different energy levels, right? So with metallic bonding, these molecular orbitals are so close in energy that they're going to look like this. Okay? Just ridiculously close in energy. They make so many that what we do to represent all of these is we just draw a box. And that's called a band. So what we have when we do metallic bonding are a few different kinds of metals. Conductors, semiconductors, and insulators. So insulators will look something like this. Okay, recognizing that these bands, that we call them, are just a lot of molecular orbitals coming together to essentially make one molecular orbital. So these are all filled with electrons. These are all unfilled. So this is an insulator. We call this the band gap. And if this is an energy diagram, it takes quite a bit of energy to excite this electron into these empty molecular orbitals, which is what makes that an insulator. So moving on to a semiconductor, it may look like this, where the band gap is smaller. It takes less energy to excite that electron up. And then finally, we have conductors. That's the filled, they have a name, I think this is called the conducting band maybe. This is the filled molecular orbital band, and this is the unfilled. Okay, so they're going to overlap. So the reason why that is so conductive is because it's going to look like this, where every other atomic orbital is filled, and so it doesn't take too much energy to excite those electrons back and forth. So, looking at band gaps there between insulators, conductors, semiconductors, that's the takeaway, yeah.
So, like, a way of thinking of it is that the electron between the two bands, like, it can't exist in between. Like, it has to be either one or the other. And so, so the further it is, the harder you need to jump.
Exactly.
So it's going to, like, if the band gap is too far apart, they're just not going to conduct energy because they can't pass it on from one electron to the next.
Yes. Yep. That's exactly correct. Yeah. Yes.
So the transition metals would have that, like, the conduction band, and then wouldn't, like, the metalloids have that, like, semiconductor?
Probably. Mm-hmm. Yep.
In problem set 22, it talked about doping.
Yep, I'm about to talk about that. Yeah. The valence band is I think the one at the top. Again, this is going to be talked about tomorrow, so it's okay. This is your first time hearing it, so I'm just pointing out what you should know, right? This one, talking about band gaps. So, the next thing we have are with semiconductors. We can make a semiconductor more conductive by doing what is called doping. And what doping is there are two types, N-type and P-type. P-type is when we replace some of these atoms with an electron, I think P-type is an electron poor atom. So what will happen is we then have an electron poor atom with an empty molecular orbital there, meaning it's easier to get to that empty orbital. Or N-type doping is when we have an electron-rich donor, or atom, which will be here, again, making it easier to jump into, essentially decreasing that band gap. So, again, for the test, and tomorrow when you go to lecture, just be paying attention to what P-type and N-type doping is. There shouldn't be any complicated question about it. And I know you guys, this is probably the first time you've ever heard of that, so just pay attention to that in lecture, go through that in his lecture slides. Yeah?
So the conduction band is the unfilled one,
I think the conduction band is the filled one.
the filled one.
It's valence bond in the band? Oh, yeah, that makes sense. Okay, sorry, valence band, cool, is in the bottom. Again, he's going to talk about this tomorrow, so I'm going to move on from it, but yeah. So, any questions? We're moving on from MO theory, VB theory, and bonding. Okay, Lewis structures. Let's first talk about resonance. Okay, resonance. Here are a couple misconceptions about what resonance is. And then there's one true thing about resonance. So go ahead and read these. Okay, which one is true? 1, 2, or 3? 2. Okay. So do not get tripped up by that. If you got that wrong, then you'll need to go back and kind of learn about resonance a little more. Resonance structures, it's a way to show a hybrid of multiple molecules. And we're gonna continue with that in just a second. So draw the Lewis structures and any equivalent resonance structures if they exist for chlorite and chlorite. You should have these memorized, right? Include formal charges, and then determine the bond orders.
Let's draw some. CO2 and CO3. I believe they both have negative charges. Totally is.
raise your hand if you need more than a minute. If you're gonna need like more than a minute. Okay, so we'll wrap up in about 60 seconds. I don't think if you're asked to draw a Lewis structure, I don't think it will be super important for you to like put it in brackets and then put the charge on the outside. That is technically what you're supposed to do, but for ions. Yeah.
So with chloride, why can't we draw with 2 double bonds?
So we'll talk about that. It's a great question, though. Unless for some reason I move on without talking about it, then quickly grab my attention. Yeah.
So when we're drawing Lewis structures, you want to minimize the formal charges as much as possible.
Yes.
So is that the reason why the reason why chloride wouldn't be like two oxygens and then like just giving like a positive charge to the chlorine and then a negative charge to the oxygen is like just kind of upset. Is that like the way to do it?
So I think I'm following you, but let me know if this confirms what you're saying. Everything wants to have a formal charge of 0, but that's not always possible. So if we have negative formal charges, we want to place them on the electronegative elements. Yeah, which tend to be the ones on the outside. I appreciate that. Okay, so before I answer a question about why we don't double bond both sides, are there any questions as to why I drew chlorate like I did? Or chloride? Okay, so I was asked and chlorine had still
Might have stopped
2
recording.
substairs. Okay, I was asked, why don't we draw another double bond? Why don't we do this? Now, oxygen's formal charge is 0 here, 0 here, 1, 2, 3, 4, 5, 6, 7, 8, and then negative 1 here. That is an excellent question. Both seem like very good Lewis structures. Why is this a less stable structure than the one we have drawn up there? Yeah?
Because you want to get the negative charge off that central atom.
Yes, if we have a negative charge, which in this case we have to have a negative charge, we couldn't get them all to 0, then it would rather be on the more electronegative element, which is almost always the ones on the outside. So, although this is considered, and we're going to talk about this is considered a valid resonance structure, it is not the best structure with the equivalent resonance structures. Yeah.
So if we were asked to draw chloride and its resonance structures on the exam,
You would not draw that.
we wouldn't draw that.
No, because what you would be asked is to draw chlorite and all, it should probably say equivalent structures, but if it just says, draw the Beck structure for chlorite, or the most stable structure for chlorite, and include resonance structures. That's more likely what it would ask. You would not include that, because that isn't the most stable. Those two are the most stable, and they're equivalently stable, which is why we draw both of them.
So would that be considered resonance still or no?
We're going to talk about that in a second. It wouldn't ask you something like this. It will ask you probably something that I'll talk about that in a few slides. Yeah.
So the formula that we used before to find the amount of bonds, where it's like the needed minus the valence, and then we divide that by 2.
Yeah.
So that just wouldn't work.
Yeah, because that's to find the bond order in molecular orbital theory. Here, we're not looking at molecular orbitals, so there's no way to know where bonding and antibonding orbitals are. So there is a way to approximate bond order using these, though. So someone tell me, because this is with the topic of resonance, right? So I've got this bond right here. What kind of bond is that? Okay, you guys are wrong.
not just like we're talking real.
It's what kind of bond is it?
Sigma pi.
It's a 1.5. Well, sorry, that one's a 1.5 bond. It's a 1.67 bond. Okay, there is where our concept of resonance structures come in. Right here, this is not a double bond. This is not a double bond. It never looks like either of these two things. And sorry, my question probably confused some of you. That's probably why you answered. But what I'm trying to get across is that chlorite never looks like the top structure. And it never looks like the bottom structure. What does it look like? It's a hybrid between both of them. So this is not, in chlorites, this bond is not a double bond. It's a 1.5 bond. And we represent that by doing these two resonance structures. Yeah?
So if you have a molecule that has like certain bonds that aren't participating in resonance, they would be included in the finding bonds.
Correct, yeah. So if we just have a double bond and you're asked what the bond order is, it's just a bond order of 2. But resonance structures is telling us that this isn't a double bond. It's telling us that it's a hybrid between both of these. Okay, so are there any questions about that concept of resonance? It's a hybrid showing the delocalization of those electrons or bonds represented in these resonance structures.
Mm-hmm. With valence bond theory to find the bond order, we're just taking the average. Basically.
With molecular orbital theory or valence bond theory?
Valence bond theory. So on this one, so to find it, you can just add it. So it's like 5 divided by 3.
Yeah. So given the Lewis structures, that's how you. Yeah. So you do 1, 2, 3, 4, 5 divided by 3. That's how you find the CLO bond order. Yep. Okay. Questions about these equivalent resonance structures? Yeah.
So if we want to draw the two other resonance structures now.
Yeah, you would. I was just lazy and I didn't want to make the picture small. Okay, any other questions? Okay, so you will see resonance used in 2 ways. The most common way, likely the only way, minus maybe one exception, that you will be asked on a test is you'll be asked this. Draw the most stable Lewis structure and all resonance if there is resonance. So that was like the one we just did. The best structure had resonance, so we drew the resonance. That means it is perfectly that those 2 molecules, right, or 3 in the case of chlorate, were equally contributing to what the molecule actually looks like. Because they were both the best, right? Both of them were better than this one for a specific reason. So that's the most common one you'll see, all right? And that's pretty much, yeah, so that's all that I talked about right there. So we just talked about that. Everything we've talked about so far, that's what you're most likely to be asked to do in an exam. Okay, so now moving on to an example that you may be asked on the exam maybe once, but then that's it. So hopefully this doesn't confuse you too much. So they may ask you to draw valid resonance structures. Now, for the purposes of this class, a valid resonance structure, which is why I kind of didn't want to include that in this example, a valid resonance structure is essentially going to be anything that is still completing the octet rule, has all the atoms fulfilling the octet rule. The only differences are formal charges. So there's 2 kinds of questions that it could ask you regarding this. So you might see both of them, but one would be pretty straightforward, right? One is it might ask you to, it might give you, so like chlorite, for example. It may give you that, and this, and then include the electrons maybe. And then, this would be a bad example because there's only 2, but let's take phosphate, for example, or nitrate. Nitrate has 3, or chlorate, that's probably a better one. And it has kind of different ways to draw it, or maybe it does this too. And it says, based off the formal charges, which of these is the most stable structure? Yes, so we just talked about that, right? You would choose the one with the most minimized formal charges, right? Okay. The more confusing one is probably them maybe asking you to draw 3 valid resonance structures for something. And So we'll do this one for now. So this is the kind of question it could ask you. Considering formal charge, what is the preferred Lewis structure of NCO minus? I'm sorry, I should have taken out the red box so you guys could practice. But let's talk about why of these 5 structures drawn for NCO, why this top left one is the best. Okay, so what is the formal charge on this nitrogen right here? 0. On the carbon? 0. On this oxygen? Okay. Really good Lewis structure, right? Only one formal charge and it's a -1. All right, what about the second one? What's the formal charge of nitrogen?
-1.
5 minus 1, 2, 3, 4, 5, 6. So -1. What about this carbon?
0.
0. On this oxygen?
0.
Okay, well, also pretty good. So how do we decide between 1 and 2? Right, and do you have to memorize that? No, you're going to be given an electronegativity table, so you just refer to that. It'll be on the last page, guys. Please don't do the entire test and then get to the last page and be like, wait, this has been here the whole time? Okay, had students tell me that. That's sad. All right, so, and then this third one, what's this formal charge of this nitrogen? -2, the carbon?
0.
This oxygen? Okay, so which one is the worst of these 3?
3.
Number 3, right? Okay, so first of all, before talking about drawing them, does it make sense how to pick number 1 given these 5? You just find formal charges and you're looking for the one that's most minimized. Everyone feel comfortable with that?
Yes.
Yeah, go on.
I have a question on the last 2. So you said the electron likes to go to the less or more electronegative atom.
The negative formal charge would prefer to be on the more electronegative atom, if you have to have a negative charge. Okay, so yeah.
There would be a situation where there's, I mean, obviously not with this one, but where the most electronegative would have a negative charge, and then say like carbon had a positive charge for one of them, and then the other one, like the nitrogen had a negative or a positive charge.
So,
Like which one would you choose if carbon had it in one, but not nitrogen in the next?
I think I see what you mean. I don't think there would be an example like that. I don't think I've ever seen one. Okay, so now let's say instead that you were asked to draw 3 valid resonance structures for NCO. The first thing that you should think about is the fact that if they give it to you like this, that's the order they want you to bond it. So you would do NCO. Okay? Your first step would be to count the number of valence electrons there are. In this case, there's 6, 12, 16. 2, 4, 6, 8, 10, 12, 14, 16. Okay, so if you're asked to draw valid resonance structures, okay, we just determined that number 1 was the best. So, and does number 1 have equivalent resonance? No, there was nowhere else we could have put that and made it be the exact same. But if you were to ask to be draw just like a few valid resonance structures, just keep everything at having an octet. So for example, you should notice that carbon doesn't have an octet, so you want to give it an octet. Well, there's a couple different things we could do, right? We could double bond both sides, we could triple bond one side, we could triple bond the other side. That's 1, 2, and 3. So if you were asked to draw this one, you would probably draw 1, 2, and 3. And then you might be asked which one is the most stable, in which case you guys already did that, based off of formal charges. So what that means, though, is that these are still contributing to what the overall structure looks like, but number 1 is contributing most. So number 1 is probably contributing 90% of what the molecule looks like, which is why we're fine drawing it like that, because it pretty much looks like that. But in reality, it's a hybrid, a weighted average of maybe 90% the top one, like 7% the second one, and then 3% the last one. And it's a hybrid between those 3. Does that make sense to everyone? Yeah. Okay, just tell me good. All right. Any questions?
So that when you drew a single bond right there, that would be valid, technically.
No, so this is where you would probably start, and at this point you would ask yourself, okay, I want to give it an octet.
Yeah.
And then that's where you would go from there.
All right.
All right, moving on. Okay, there's only one kind of math question that you could possibly get on this exam. All right, and it is something like this. You should still be able to convert from grams to moles, moles to number. All right, so give this one a go. How many bonding electrons are in 10 grams of sulfur dioxide?
All right. Watch out. Here we go. Who gets the first speed test? This exam is timed.
Wait, sorry, I want your attention one more time. If I were to ask you to draw 3 resonance structures of this, what if I did this? And then went from there. Could I do that? No. Why?
Different molecules.
Those are different molecules. In fact, what are these? Isomers. What kind of isomer? Okay, is everyone paying attention to me right now? If I were to ask you what kind of molecules these two are, don't just say isomers. Say constitutional or structural isomers. Yeah. Yes, they're not the kind of resonance structure that you're going to see on literally every single question, except like a couple exceptions on the exam. But they are still considered resonance structures, just not equivalent resonance structures, because they have different formal charges. The ones that are equivalent structures resonance structures have the same formal charge. If that makes sense.
Two molecule weighs its molar mass of 64.02. Incredible. 64.062. Yeah.
Is it your laptop, Chase, or is that?
Jason.
Okay.
But his knees hurt, so I had to get stuff for him.
I appreciate that.
Yeah. He got surgery.
For the sake of all of the students who can't make it, we're going to rewatch this.
Yeah.
I hope your laptop, you should check this. That's good. Okay. So it just be 8 times 64 divided by. Well, I thought it was grams. So wait. There's 8 bonding electrons per molecule, which you multiply it by 64 grams per molecule. Right? Well, per mole. Of this molecule.
I'm doing the dimensional analysis. I got
That makes sense.
doing it right.
You also have to do how many electrons.
No, you have to do how many bonding electrons, which I'm doing right now.
There's
8 bonding electrons. But just to make sure. Well, sulfur dioxide.
Yeah, we'll have to.
So, start with here, wait,
Because in one
Or if it makes more sense to you, in one mole there's Avogadro's number of molecules.
Which
and then in one
each
molecule
molecule
there's
has.
That's what I
it's the same exact thing.
Incredible. We got it.
In the 8 oceans, there are.
Okay, raise your hand if you're done. Okay, raise your hand if you need just one more minute. Okay. And throw out the right answer.
Oh, that's what it's.
Yeah. On the test, this probably would be a first question, and there's very likely no math questions at all. Yeah, in future exams, it's like a hit or miss whether they actually care about the issues or not. Like even within the exam itself, like sometimes there'll be like one free response question where it's like half of an opposite, and then like all the other questions it doesn't say anything about the correct yeah, so like for the first exam, that's what here and now. As long as it's right. Okay, raise your hand if you want more time. Okay, cool. So, this is a difficult question because it's also a relatively difficult Lewis structure to draw. So are there any questions about why sulfur dioxide is drawn like this? Okay, and then any questions about the math there? Yeah.
So can you go over why there's 8 bonding electrons?
As in why the Lewis structure looks like that, or why I'm getting 8 from that Lewis structure?
Why are you getting 8?
Okay, so each bond has how many electrons?
2.
2. So there are 2, 4, 6, 8.
Okay.
Yeah. Explain the Lewis structure? Yeah. So if I were to start, we're trying to stay as close in the middle as possible for the video. So sulfur dioxide has how many valence electrons? 18. So I've gone 2, 4, 6, 8, 10, 12, 14, 16, 18. Number one thing to think is, okay, well, I should probably give sulfur an octet. Doesn't really matter where I take it from. I'll do this side. Okay? So now let's check formal charges. What's the formal charge in this oxygen? This sulfur? This oxygen?
-1.
Okay, not a bad structure, but at this point you should ask yourself, is there anything else I could do to minimize those formal charges? And maybe before asking yourself that, you should ask, is sulfur allowed to expand its octet? Because if it can't, then there isn't anything else we can do, and we're stuck here. But sulfur is in the 3rd row, and if it's in the 3rd row below, it can expand its octet. So then we should be like, oh well, what if I then do another double bond? Now everything has a 0 formal charge, which is exactly what it wants to be. Wants to all be a 0 if it can. That answer your question?
So then why is that?
I don't want the -1 on the oxygen. I have them all at 0. Do you mean when I was talking about earlier having a -1 on oxygen? Yeah, so here's the number 1 rule. You want everything to be at 0. But rule 1A, if it has to have formal charges, because sometimes we literally can't get everything to 0. If it is going to have formal charges, then we prioritize where they will be by putting the -1 on the most electronegative atom. And that will be better than having the negative somewhere else. But having them all at 0 is the best. But sometimes that's just not possible. Yeah?
Will a positive charge want the least electronegative?
Yes, exactly. Which will generally be the central one. Okay, moving on. Alright, if you don't know how to draw Lewis structures, okay, you will not do well on this test. Because Lewis structures tell you so much information. So maybe like half the test has a Lewis structure in it. Okay? So there's a lot of information, right? You can do all of these things, molecular geometries, bond angles, knowing the polarity, hybridization, even into valence bond theory, right? So you got to know how to draw Lewis structures. So let's talk about these. Do you guys want to do these right now? Because, I mean, they're posted. I just don't want to waste your time.
Yes.
Okay, raise your hand if you want. If we want to do these.
Yes.
Okay, it's probably only like half. So I'm going to have you guys do 2. Do KR, BR4, and NI3. These last 2 are pretty easy. Okay, just do the first 2. Krypton, tetrabromide, and nitrogen triiodide. So again, these are more simple Lewis structures with no resonance or anything, because the important one here is going to be bond angles and geometries. We're going to be focusing on that. So hopefully these ones go by a little fast. For those of you who don't want to draw the Lewis structure, you just want the practice, there are the Lewis structures. Maybe try not to look at the rest of them if you want the practice doing the rest. Yeah. I'll talk about that. Okay, I'm going to bring you guys together real quick. I know I didn't give you too much time, but again, it's just Lewis structure practice, so you could practice that on your own time. But just to make sure, are there any questions as to why the Lewis structures look like they do? Okay, good. So, geometries, you have to memorize them, okay? It's partial memorization and partial knowing what they look like. Square planar, if you know that it stems from an octahedral molecule, it makes sense that it's square planar because it's literally a square on a plane, right? So memorize these, okay? These are very important because geometries then help you determine the polarity and the bond angles, okay? So what's the bond angle of all of the bonds in an octahedral electron geometry? 90, okay? So the bond angles in all of those molecular geometries, no matter how many electrons there are going to be 90. For Ni3, that stems from tetrahedral, standard number of 4, so it'll be 109.5. Again, the next one, 109.5. And again, the next one, 109.5, okay? You have to know those bond angles. Now, let's talk about why I have these less than 109.5s written, okay? So, it's not important for you to know the exact number. In fact, I wrote less than 109.5 for something I'll say in a second, but if you just wrote less than 109.5, that would still be correct, okay? So, someone tell me why, though, is this less than 109.5? Because there is a lone pair. Lone pairs take up more space, and so they kind of push the atoms down, giving it slightly less than 109.5. Now, you may be asked, which bond angle is the smallest? In which case, you'd want to recognize, right, that since H2O has 2 lone pairs, it has an even smaller bond angle than 109.5 than Ni3 would be, since Ni3 only has one lone pair. So again, you don't need to know the exact bond angle, but know that it's going to be less than, and be able to rank those last three if you needed to. Yeah?
Since there was a double bond on like the tetrahedral, for example.
Double bonds technically also take up more space, but
they write like the spoolie thing.
yeah, and we didn't really talk about it. So electrons take up more space than bonds, and so they're more important. And I would just say don't worry about it.
So
But you
there
wouldn't.
was a double bond, we just write 109.5.
Yeah, but you wouldn't be wrong if you said less than 109.5.
Okay.
Yeah.
Could you just briefly explain how to determine like the polarity of the molecule as a whole?
Yep. Okay, are there any questions about those bond angles, geometries, or the Lewis structures? Yeah.
On the test, will it specify which angle it wants? Because like there's some geometries that have.
So it will always be less than, right? So we're never talking about the bond angle that goes above the electrons. So it'll always be less than. Other than that, there's only one example where there are different bond angles, but only one. And that's with a trigonal bipyramidal molecule, which stems from a steric number of 5. What's the bond angle of the trigonal planar section of that molecule? 120. And then the top are these two? Yeah, 90. That's the only one where they'll be different, in which case they would probably just say, draw all the bond angles, in which case you just include 2. Okay, so now let's talk about polarity, okay? Polarity of the molecule. If the molecule is symmetric, what is the correct way to say that? If the molecule is symmetric, it will be non-polar, okay? So is krypton tetrabromide, is that a symmetric molecule?
Yeah.
Right, those bromines are all on opposite sides, so that will be non-polar. What about nitrogen triiodide? No, it is not symmetric. We introduced a lone pair, making that non-symmetric. What about H2O? That will be polar, okay? So here's what we have going on right here, all right? Any of the electron geometries, as long as it's surrounded by the same kind of atom, so I'm not talking about CH2Cl2, I'm talking about something that would be like CH4 or CCl4. All of those will be nonpolar because all of the electron geometries are symmetric.
Yes.
All of the other ones with lone pairs, those will all be polar with 2 exceptions. Your square planar geometries and your linear geometries. Which is obvious, right? A linear geometry is clearly symmetric. The square planar as well is pretty obviously symmetric. So, that's a good way. You could just memorize that if you wanted to, okay? Literally all the electron geometries are going to be nonpolar as long as it's surrounded by the same atom. And then all of the lone pair molecular geometries will all be polar except for square planar and linear. Yeah?
So I believe we talked about at some point certain types of bonds that aren't polar ever, and so, like, for instance, I believe hydrogen-carbon is not polar.
So, here is one example that is less intuitive, okay? Let's talk about ozone. Ozone is O3, and I'll draw a Lewis structure for you. You'll find that there is a lone pair up there, and then it looks like this. Is an oxygen-oxygen bond polar, non-polar? What is it? It's completely non-polar. Electronegativity difference is 0, okay? But, given what I just told you, you're going to go off of that rule still. Even though this is a completely non-polar bond, you will still consider this molecule polar. Because it's very slightly polar. In fact, when I took this class, they had the right answer in the key as being a non-polar molecule. So, it's a little ambiguous, but it is very slightly polar just because this lone pair of electrons are on top. And that is the truth, that it is still a polar molecule. It's just very slightly polar. So, just know, again, the geometry. If the geometry is symmetric or non-symmetric.
In what direction would that be polar?
I assume it would be where the electrons are. You're very unlikely to be asked to draw dipole arrows or anything, though. Just ask literally nonpolar or polar. Yep.
So I can see how that will have a dipole.
Yeah.
But like, if I'm like, so polar is when it has the difference in electronegativity over 0.4, right?
So you are now talking about bonds, but yes.
Okay, so I don't understand how that would be polar. I mean, I understand how it's not symmetrical because the
this
electron
bond is a nonpolar bond because the electronegativity difference is less than 0.4.
Yeah.
That's just a bond.
Yeah.
But now, separate subject, now when talking about polarity of molecules, we're going to just look at the symmetry of the molecule.
Okay, got it.
Yeah. Okay. So, one example, just for fun. Is that polar or non-polar? Non-polar, polar. Raise your hand if you think non-polar. Raise your hand if you think polar. Okay, all you non-polar folk are wrong. You are thinking that these two pull in opposite directions, right? Are these 180 degrees apart from each other? No. What kind of molecule is this? Geometry. It's tetrahedral. I'm fine drawing the Lewis structure like that. Totally fine. Doesn't matter if I draw the Lewis structure like that. But recognize that that is not actually what it looks like. It looks like what I have up there, which you can actually see is, you know, those chlorines aren't pulling in opposite directions. They are going to be pulling on one side. But again, if they were all chlorines or all hydrogens, then yeah, that would be non-polar. Okay. Any further questions before I move on?
Yeah. Because the actual
Okay. Nomenclature and isomers. Okay, so I have functional groups on here, but they got rid of that, so don't need to know those functional groups. Naming. You have 3 different kinds of naming. You should always ask yourself, is this ionic, covalent, or an acid? Okay, there will always be, and this will likely be a free response question, where they give you 8 formulas, and you have to do the name, and then 8 names, and you have to draw the formula, okay? So, I've been kind enough to include a ton of examples for you guys, practice. But make sure you identify which of those 3 it is first, because your naming rules are very different. Making sure you memorize the polyatomic ions and the elements. Okay, like lead, mercury, silver, gold, right? Yeah, they're not as straightforward as C is carbon, you know. Okay, so you guys want to do practice, I assume?
Yeah.
Okay, okay, we have enough time. Raise your hand if you want to, well, so 2 options. 1, just straight into practice. Or option 2, I talk about the naming rules for all 3 pretty quick, and then you go into practice. So, option 1, raise your hand. Option 2, raise your hand. Okay. So, in this case, in order to determine if it's ionic, covalent, or an acid, you could take the electronegativity difference, right? But don't do that, especially since you're likely going to get a lot of examples that you need to name, okay? For the purposes of naming, you can just say, is it a metal with a non-metal? Yes? Then it's an ionic compound. Is it non-metals, things on the right side together? Great, it's covalent. Is it hydrogen with an anion? Great, it's an acid, okay? So just go off of that and you'll be fine. Yeah? Yes, because those are polyatomic ions. But those polyatomic ions will be paired with a cation forming an ionic compound. Okay, so I'm going to talk about the 3 rules. First one is covalent. Covalent naming is very easy. If you have determined it's a covalent molecule, let's point them out real quick. Is HI covalent, an acid, or ionic? Acid. Na2S.
Ion.
An ion. Phosphorant. That HBr.
Acid.
Acid. P4O5. Covalent. Okay. Actually, let's Someone name SO4 for me.
Sulfate.
Wrong! I love it! Love telling people they're wrong. It's not sulfate. Why is that not sulfate?
It's not charged.
Because it's not charged, okay? Wouldn't that be mean if they threw that on a test?
Yes.
Yeah. So, SO4, what is that then?
Sulfur.
Tetroxide.
Yeah, sulfur tetroxide because it's a covalent compound, alright? You guys are going to get all excited because you're like, boom, I've memorized polyatomic ions, I know what SO4 is, so you'll say sulfate. Don't do that, please. It'll be sad. You'll get your test back and you will be, it'll be disappointing because they tricked you. That's sad. But, so, covalent, alright? So, hopefully you know that you've been able to separate them first. All you do is you take the first element, so you do prefix, element, prefix, element, I. Very easy, okay? Our prefixes being mono, di, tri, tetra, and so forth. One weird thing about this one. If the first... So you'll never see mono with the first one. So CO2 is not monocarbon dioxide, it's just carbon dioxide. So, our examples, right? CO versus CO2. Carbon dioxide. Carbon monoxide. So we say mono because there's one oxygen, but we never start with mono. That's like just the one weird rule. But it's almost intuitive. You almost do it without thinking that you're doing it. Okay? And that's it. Pretty easy, right? So now let's do ionic. You've got your simple metals with nonmetals. Left side of the periodic table to right side of the periodic table. How you do those are you go cation, and then anion, I. So, NaCl, sodium chloride. Easy, right? The one thing that you want to watch out for throughout this entire, that applies to both ions and acids, is that when you're going backwards, if I say magnesium chloride, you need to make sure you go Mg and Cl, right? Cl has a minus, Mg has a 2 plus. So when writing the formula, you must do MgCl2. Why don't we say magnesium dichloride? Because different rules from covalent, right? This is the only one we do prefixes for. Never, ever, ever say magnesium dichloride. Because we don't, so why don't we say magnesium dichloride? Don't we have to indicate how many chlorines there are?
No, because it's implied that there's charges.
No, yeah, because the charges let us know how many there are. So, don't need them. Okay, so those ones are pretty easy. Now let's get into a little more complicated, because they could be cations with polyatomic ions, right? There's only one difference. Instead of changing the name to "ide," you just want to say the polyatomic anion's name. So, you'd say the cation, and then the polyatomic name. So sodium chlorate, Na, ClO3. It was a plus and minus, so I didn't need anything there, right? So I don't say chloride, right? I say just the name of the polyatomic ion. So you got to memorize those. But again, they follow pretty much the same rules.
So is sodium chloride?
Yeah, sodium chlorate. Okay, now one more. Transition metals. Now we're getting a little weird. If I say iron oxide, what's the charge of oxygen? What's the charge of iron? You don't know, okay? So in this case, the charge doesn't, or just saying it doesn't actually tell us how many of each there are going to be. So for transition metals, they indicate the charge using Roman numerals. So if I tell you Fe2O3, the name of that is not just iron oxide. Since it's a transition metal, you have to figure out what the charge is going to be on that iron. So what's the charge of oxygen? 2. What's the charge of iron then if I had 3 oxygens?
3.
plus 3. So the name would be iron 3 oxide.
In parentheses.
Yep, and then you put it in parentheses.
And that's for all transitions?
Yep. So cation, Roman numeral,
Except for zincs.
anion, I.
Zinc only has 2 plus, so it's always.
Yeah,
It's
you
index.
probably wouldn't be wrong if you still included a Roman numeral on that.
But I know that.
Okay, yeah.
For your cation, for your poly.
Yeah, the poly, yeah.
So like you still have to balance it, right? You did, like,
Yep, yeah, this entire time you still need to be balancing everything.
So it's like 40 cents.
Yep, exactly. So if it was sodium phosphate, it would be Na3PO4. Okay, so now let's do our acids. Alright, so there's 2 ways to name our acids. We either have acids with just a monoatomic ion, so just what we see up there. And those ones are easy to name. We say hydro, blank, or element, ic, acid. Hydroelementic acid. So what's HCl? What's HBr? Hydrobromic acid. Easy, right? Remembering hydrosulfuric acid is what? Okay, it's not HS, it's H2S. Remembering this whole time that you want to make sure you're balancing charges. Right? That's kind of the one thing that applies to both of these. Make sure you're always balancing your charges. Okay, so those are easy. We can also have hydrogen with a polyatomic ion. In that case, a lot of our polyatomic ions end in 8 or ite. So if it ends in 8, we change it to ic acid, and we take ite, and we change it to us acid. So you tell me, what is hydrochloric acid? Okay, so raise your hand if you said HClO3. Raise your hand if you said HCl. Okay, so less than a quarter of you, or more than 3/4 of you, didn't answer. But if you're thinking HClO3, then you are wrong. Okay? I said, what is hydrochloric acid? And your mind, again, probably said, haha, I have memorized the polyatomic ions. Chloric, chlorate, ClO3 minus, got it. Someone tell them why that's the wrong train of thought. Hydrochloric acid, okay? When you say hydro, that does not mean acid. Hydro means it's one of the monoatomic acids. So hydrochloric acid is what? HCl. Chloric acid is HClO3. Okay, that's why we distinguish them with that hydro, because we have chloric acid and hydrochloric acid, sulfurous acid and sulfuric acid and hydrosulfuric acid, phosphoric acid and hydrophosphoric acid. Okay, we have all 3 of these polyatomic ions that make them very tricky. Okay, so hydro does not mean acid. That should be your indication that it's a monoatomic. So, with that being said, though, everyone pay attention. Do you guys know what the name of Cn minus is?
Cyanide.
Okay, does that end in 8 or ite? Okay, so that's one of the few examples that we're actually going to name that like the top one. We would say HCN is hydrocyanic acid.
So are ions hydrochic then?
I think all of them probably are. Yeah. But HCN is the only one that I've seen. Okay, so hopefully that helped. Now let's do maybe just these practices, and then we have just isomers left. Let's go through them one by one at a time, actually, okay? Because I'll let you guys do this next page by yourself. Not in class, not in this review, but let you guys have a go at it. But so let's do this together. What's HI? Right, and I'll go ahead and point at the rule, right? Hydroiodic acid. Okay, Na2S. Take a second to think about it. Okay, what is Na2S?
No, sodium.
So why isn't it sodium disulfide? Right, because it's not covalent. So your first train of thought should always be, is it covalent, ionic, or an acid? So it is sodium sulfide. Okay, what about phosphorus acid? Think about it for a second. Phosphorus acid. Okay, so what is phosphorus acid? H3PO3. Okay, are there any questions so far as to these first few? Yeah. Why isn't phosphorus acid H what? Because phosphite is PO3 2 minus. Yes.
Wait. Phosphite's PO3 2 minus?
PO3 3 minus. I said 2 minus, I apologize. Phosphite is PO3 3 minus. Phosphate is PO4 3 minus. Okay, moving on. HBr. Think about it for a second. And hydrobromic acid. HCN. Hydrocyanic acid. Carbon tetrafluoride. CF4. P4O5. Tetraphosphorus pentoxide. Sulfur trifluoride. SF3. Sulfurous acid.
Hold up. It's SO3 2 minus.
So this is my hydrogen.
H2SO.
Sulfurous stems from sulfite, which is SO3 2 minus. So it will be what? H2SO3. SO4. Sulfur tetroxide. If you're in my class and you say that's sulfate, if it were to show up on a test, I will throw chalk at you. I can't throw chalk at the rest of you, but I would. Okay. Lead 4 sulfide. This one you probably need to think about for a second.
PB
Okay, and so it will be PbS2 in order to balance out those charges.
Wait, how do you know what lead is?
Because you have it memorized.
It's peanut butter. Don't listen to
It's not peanut butter. I've seen that so many times on tests. Like more than 10 times on tests. Did I give them half credit? Sure. It's funny. But not full credit though. Okay? So just make sure you know all of them, alright? Okay, are there any questions with these ones that we've done so far? Okay, we can go back and do these last ones if we have time at the end, but I want to get to isomers first, and then chiral carbons, and then that's it. Okay, are there any other questions? Okay, isomers. Here's the thing, people really stress out about isomers. They're probably not a big deal on the test, okay? Here's the really important things to know. Constitutional and structural. Be able to recognize those. It's a different connectivity, right? We talked about that already. Where if we're rearranging the atoms, those are structural isomers. Enantiomers or chiral molecules, those are let's talk about chiral centers first. So, a chiral center, true or false, is a carbon attached to 4 different atoms. True. False. Okay, love it. Someone tell me why that's false now. Okay, so let's take this carbon for example. Is that carbon chiral?
Yes.
Okay, it's bonded to 2 carbons, but that is not the definition of a chiral center. And half of you are probably like, hold up, That's what I was told, okay? But it's probably not what you were told, unless the TA told you that, and then that's bad. But it is a carbon attached to 4 different groups. So we are literally going to look at the rest of the molecule. So is this different than this?
Yeah.
Which is obviously different than the other 2 groups. So that is a chiral carbon. Even though they're both carbons. Because that doesn't matter. You're looking at the rest of the rest of the molecule. If those 2 are different, then it's chiral. Yeah.
So they wouldn't have been considered groups, the left and right, if they had the same structure.
Yeah, so if I did that, are those the same groups?
Yes.
Yeah, those are now both CH2, CH3 groups. So now that's no longer chiral. So what enantiomers are is if you take a molecule that has a chiral carbon, the mirror image of that is then an enantiomer. And that's what an enantiomer is. Yep, yeah. Then we have cis-trans molecules, which are pretty easy. They are molecules with double bonds, where the double bond is arranged slightly differently. So this is a trans isomer. This is a cis isomer. Because double bonds have restricted rotation, so it actually matters what direction it's facing. Okay, any questions with isomers? Okay, so now let's do some of that chiral carbon practice. Go ahead and circle all the chiral carbons, or identify how many there are.
Which ones are chiral? The chiral carbons have 4 different groups attached to them.
Oh, so they can have 4 bonds.
4 groups would be around. 4
Okay, there's that one. That one.
We gotta think about the
That one. Dude, I got it right.
Wait, are there any hidden heads? Yeah, there are.
They're all hidden.
Okay, let's take it step by step together, okay? Is this carbon chiral?
No.
Okay, anything attached to a double bond is not going to be chiral, right? Is this chiral?
Yes.
Yes, all right. Pretty much anything is going to be chiral if it is not attached to a double bond and not only attached to 2 things right here, right? Because why is this not chiral?
2 hydrogens.
Right, because if it's only bonded to 2 things visibly, then there's 2 implicit hydrogens, right? So, chiral right here, right? No? Yes?
No. No, that's an oxygen. No. Nah. Yeah. No.
No. Okay, everyone feeling okay about that?
So there's 3.
Okay, that's all I have. So, are there... Yeah.
Are conifers considered?
Not really.
What was it?
You might find some textbooks that say they are, but... No, probably not. Yeah.
So funny.
No, that was a lot. Okay, but it's important now. I should. At least for like lots of
Yeah, you're welcome.
Thank you.
No problem.
Yeah.
Hey, Chase.
as it's called.
Still recording. I just wanted to apologize if there's any bantering going on in the video. This guy is an idiot.
Yeah.